Okay, we're looking at 0654 summer 2019 paper 6-1, question 3 this time. Alright, first one about physics. We know it's about physics because it's about a pendulum. Alright, pendulums are the physicist's best friend. It can do a lot. First one, really easy to miss what you have to do here. You have to draw something. You have to draw an accurate line to show the length of the pendulum. Okay, now, point here. The length of the pendulum is given from where it starts, right about here, to the middle of the ball. Okay, you are expected to show something. Now, it's not the length from the bottom to the top of the ball here, it's the length from the middle to the middle. Okay, the easiest way for me of doing that, taking our ruler, okay, again, anytime you're asked to do this, use a ruler, okay? Try and draw a straight line from here to here, some dashed lines from here to here, and then straight line between the two. That's our L. Follow the instructions they've told you, okay? The exact end points and start points should be marked with arrows. You need to draw some arrows, okay? You should also label it. If you didn't do that, then they are quite within their rights to not give you the marks. That would be a shame, as this is a fairly nice one to get. Okay, we're then told the setup of the experiment. We're adjusting the spring so the length is 40. We're then going to allow this thing to oscillate backwards and forwards. Oscillate basically means vibrate, means completing one cycle from right and back to left again. X through to Y and back to X. So, we're then asked to do a bunch of calculations. Okay? You're asked to calculate the mean time for 20 oscillations. You're given 3, and you should know that to calculate mean, add these numbers together, divide them by 3. There is an instruction in the paper which is to calculate the 3 significant figures. Okay? That is just sound advice in general, so please do it whilst you're doing your calculations. So for example here, not much space for me to do this, 25.5 plus 25.7, 25.4 divided by 3. I came up with an answer of 25.53. I wrote the 4 significant figures here and I wrote the 3 here as well. Okay, similar here. I think we're okay with all this. Okay, we're just simply taking the numbers we're given. Firstly, my average time. Yeah, we're then asked to calculate the time for one oscillation. Well, this is the time for 20. You need to then divide that time by 20. Again, giving answers to 3 significant figures. You're then asked to square t. Oh, I squared it, I got 1.64. You're then asked this bit here. Now, this is where I was a little bit, got a bit ahead of myself when I did this, is that you're given a length which is in centimeters, and then you're then asked to calculate something in meters per second squared. Now, my first temptation when I did this was to convert between centimeters into meters, because that's what we do often. All right, you do not need to do that here. The reason is they have already included the conversion in this 0.395. Now, the way you know that is if you decide to convert to meters here, then you're going to get a value for acceleration which would be 100 times smaller than this. You'll get 0.0963. Now, if we think about the value of g on Earth, we're always told it is 10. Yeah. So if you are getting out a number 0.0 something, you've done something wrong, and in that case it would have been changing. All right, so I think that can be a bit confusing. I wanted to change this into meters, I didn't need to. You got 9.63, you're asked to do again for another value of length, that's 80 centimeters. Okay, we get 9.75. Small thing to notice, you notice that my precision, okay, my accuracy is getting better as I go for a greater length. That's going to be relevant later. Okay, we've got our values of g. Okay, the actual value of g is 9.8. I know in GCSE we use 10. That's because the assumption is that 10 is a much easier number to deal with for quick calculations. Okay, it's not that they think you're too stupid to deal with 9.8. I think we're all fine with that. We've got 2 values. We've got 9.63 and we've got 9.75. Okay, so let's just tell you what, let's just pretend that g is equal to 10. There's a reason for this. You're asked to state whether it agrees within the with the limits of experimental error. In physics, we say experimental error is about 10%. Okay, so what that means is I could be above or below g by 10%, as long as I'm within that range, it's okay. Okay, so if we look at that, if we just said G is 10, well, 10% of 10 is 1. So I could be 11, or I could be down to 9. Whoops, I miswritten here. Okay, I'll just change that. Okay, I could be at 9 and I could be 11, I'd still be happy. That's 10% to the left and 10% to the right. Okay, well, let's look at our values here. 9.75 comes somewhere here. 9.63 comes somewhere here. Okay, so experimental error or experimental range is about 10%, meaning an acceptable range would be plus or minus 10%. Okay, between 9 and 11, not 8 and 10 as I wrote before. Apologies about that. The two values that we've got lie in this range, and so they're acceptable, and so that they agree. Last one, suggests why it's better experimental practice to use longer lengths of pendulum. Now, as we've just said, the longer length gave us a value which was closer to G. Okay, so you might be tempted at this stage to say, well, using a longer value of length means I'll get a better number. Again, I've said this before, don't say that. Okay, don't say it's a better experiment. Don't say that the experimenter is better in any way. Really, we want to think about why. And the reason for this is that when we've made two measurements here, one of them is our length and the other one is our time. When you use a lot greater length, as L goes up, you should have seen that T goes up. Now, there's always uncertainty in our measurements, and what uncertainty means is that this one might be wrong and this one might be wrong. Okay? Whenever you're doing with time, there's an uncertainty which comes into it, which is your human reaction time. And what you may be aware is that human reaction time is usually the same. It's about 0.2, as long as you're not drunk or have had too much caffeine. Okay? Human reaction time is usually about 0.2 seconds. Now, if you notice, if we go for a larger length, that means we've got a larger time. That means, relatively speaking, this 0.2 is much smaller. It's still the same, but as a percentage, if T goes up, then the percentage of 0.2 to T is going to go down. So what we're saying is, by performing an experiment with greater length, T gets bigger. And this means that the reaction time gets relatively smaller. And if reaction time gets relatively smaller, you've got a better experiment, and G is going to be closer to the real value.